power in your house, in North America, oscillates at 60 hertz.
Right, 60 hertz. That means 60 complete electrical cycles are passing through your phone charger, your lights, everything, every single second.
And if you're hearing that, 60 cycles per second, your first logical thought is that the machine generating it must be rotating at 60 revolutions per second.
You do the math on that, 60 times 60. And that's a blistering 2,600 revolutions per minute. 3,600 RPM.
And that assumption is actually correct for some power plants. The ones powered by gas or steam turbines, they absolutely scream along at 3,600 RPM.
But then you see footage of a huge hydroelectric dam. Yeah. And these massive structures harnessing a slow, powerful river. Those turbines are not screaming.
Not at all. They're enormous. They move with this kind of majestic, slow power. They might be turning at, say, 900 RPM, maybe even slower, like 360 RPM.
So there it is. That's the paradox we have to solve today. How can a generator spinning at a relatively slow 900 RPM produce the exact same 60 hertz electrical frequency as a sleek turbine spinning 4 times faster?
Our mission for this deep dive is to figure out the really elegant mechanical and electrical tricks that decouple that rotational speed from the final electrical frequency. It's a story about magnetic geometry, it's about physical limits, and most importantly, it's about something called the magnetic pole.
And to get there, we've pulled together, a whole range of sources. We're looking at foundational engineering principles from old naval training manuals, some deep technical specs on AC generators, and even historical notes on how we ended up with these utility frequencies in the first place.
We're going to explore the anatomy of a generator, the core frequency formula, the physical reasons for high-speed versus low-speed designs, and then, the ripple effect all of this has on literally every electric motor plugged into the grid.
Okay, let's start at the very, very beginning. The root of all of this, it doesn't matter if we're talking AC or DC, the physics behind generating electricity is the same.
It is. It all comes back to magnetic induction.
Michael Faraday's big discovery.
Exactly. Faraday's law of induction. It basically says you can create a voltage, an electromotive force, or EMF in a wire, as long as there's relative motion between that wire and a magnetic field.
So you can either move the wire through the magnet's field,
or you can move the magnet past the wire. It doesn't matter which one moves. As long as the magnetic lines of flux are being cut by the conductor, you will induce a voltage.
Simple enough. And to make that happen in a real machine, every single generator has to have 2 essential parts to create that motion.
Right. And they're universally called the rotor, that's the part that rotates, and the stator, the part that stays stationary.
Okay, rotor and stator?
And the big engineering question, the one that really defines the design, is which part gets the magnet, what we call the field, and which part gets the coils of wire, where you collect the power, which we call the armature.
We'll circle back to why that choice is so critical in a minute. But first, we need to be really clear on what makes alternating current, AC, so different from direct current, or DC.
Well, DC is pretty easy to wrap your head around. It's like water in a pipe. It flows steadily in one direction. Think of a battery.
Positive to negative, that's it.
Right. AC is, it's much more dynamic. It's designed to periodically reverse its direction of flow. And at the same time, its strength, its magnitude, is constantly changing.
And if you were to plot that voltage over time, you get that classic, smooth, up and down shape.
The sine wave. And that shape isn't arbitrary. It's absolutely fundamental to how the power grid works, and it's a direct result of the physics of rotation.
Okay, break that down for us. Why a sine wave? Why that specific shape?
So imagine a magnet rotating past a stationary coil of wire. The amount of voltage you generate at any instant depends on the rate at which the magnetic field lines are cutting the wire.
The rate of change.
Exactly. The voltage is highest when the magnet's pole is moving past the wire at a perfect right angle perpendicular. That's where the flux is changing the fastest.
And the voltage drops to 0 when?
It drops to 0 when the magnet is in a position where its field lines are moving parallel to the wire. In that instant, no flux is being cut, so no voltage is induced.
I see. So the voltage rises and falls based on the angle of the rotor.
Precisely. And the mathematical relationship between the angle of rotation and the rate of flux cutting is a sine function. So at 90 degrees of rotation, you get peak positive voltage. At 180 degrees, you're at 0. At 270 degrees, you get peak negative voltage, and so on. This smooth, predictable sine wave is just way more efficient for motors and transformers than some jagged square wave would be.
Let's talk about a simple way to take back your privacy and secure your connection online. Okay, let's get right into it. Right now, your internet provider sees every single thing you do. And the difference is, honestly, night and day. Without a VPN, you're totally exposed. With one, you're invisible. So, what exactly is a VPN? Just think of it like a secure, private tunnel for your data.
And here's how it works. You connect, it encrypts, and then it reroutes your traffic. Simple.
This gives you some new superpowers. First up, way better security, especially on that sketchy public Wi-Fi. Next, you get total privacy. It stops your internet provider and websites from tracking what you do online.
And finally, freedom. You can change your location to access content from anywhere and even find better deals.
All right, so which VPN should you choose? Let's look at two of the absolute best, starting with ExpressVPN. And look, the experts all agree. It's consistently called out for being super reliable and incredibly fast. They've got servers in 105 countries, top-tier encryption, and their trusted server tech means zero data is stored. Okay, our second top pick is NordVPN, and these guys are known for one thing: unbelievable speed.
And PCMag really nails it here. They praise its huge collection of servers, which is a big deal.
It's got over 8,400 servers and comes with Threat Protection Pro to block malware and ads. So here's the bottom line. Both are amazing choices. It really just depends on what you need. Look, both are at the top of their game, which is why we fully endorse them. And get this, both services give you a 30-day money-back guarantee. So it's totally risk-free. To get you started, just check the description below for links to the latest deals and offers.
This is your chance to control your digital life. So, are you ready to take it back?
And this rotational movement is what gives us the key mechanism of AC, the actual reversal of current.
That's it. Imagine the rotor has a north pole and a south pole. As that north pole sweeps past the conductor in the stator, it induces, let's say, a positive voltage.
Okay.
But as the rotor keeps turning, right behind the north pole is the south pole. It sweeps past the exact same conductor. But because its magnetic field lines are pointed in the opposite direction,
It induces a negative voltage. The current has to flow the other way.
exactly, it reverses direction because the magnetic flux is now cutting the coil in the opposite direction.
So that whole process from peak positive down through zero to peak negative and back to zero, that's one cycle.
That is one complete electrical cycle.
Which brings us to probably the most rigid, most important number in all of electrical engineering.
Frequency, measured in hertz or hertz. It's just a count of how many of those complete cycles happen every second. In North America, the standard is 60 hertz. 60 full back and forth cycles every single second.
And it's 50 hertz in most of Europe and other parts of the world. And what's so critical here, but you really have to understand, is that this number 50 or 60, it's not a guideline. It is absolutely fixed. It is non-negotiable for the grid to stay stable.
The entire power grid, every motor, every transformer, every protective relay is tuned to that exact frequency. Even tiny deviations can cause huge problems. It's not just a technical spec, it's the very heartbeat of the grid. If the frequency drops, generators can get overloaded and you risk a cascading blackout.
So every single power plant, whether it's nuclear, coal, hydro, or wind, has to feed the grid at exactly 50 or 60 hertz. This absolute requirement is what forced engineers to come up with the brilliant pole count solution we're about to get into.
Absolutely.
Okay, so to really get that solution, we need to look a little closer at how these generators are actually built. We've got the rotor and the stator. Now let's assign the electrical roles, the field and the armature.
Right. So the field is just the part that creates the magnetic field. It's the magnet. The armature is where the voltage is induced. It's the output part of the machine. And historically, engineers tried two main designs based on which part rotates.
The first one sounds like the most straightforward, the rotating armature alternator.
In this design, the armature, the big coil where you're generating thousands of volts, is the part that's spinning. It rotates inside a stationary magnetic field.
It sounds a lot like a DC generator.
Structurally, it's very similar. The big difference is that instead of a commutator, which flips the AC to DC, it uses smooth metal rings called slip rings to get the AC power out.
But our sources say this design is almost never used for large-scale power. Why not? It seems simpler.
It comes down to one thing: safety and reliability. When you're generating power for the grid, you're talking about extremely high voltages and current.
Tens of thousands of volts.
Exactly, and trying to get that kind of power off a rapidly spinning rotor through slip rings and cotton brushes is, well, It's a nightmare. You need massive amounts of insulation on the rotating shaft, and there's a huge risk of high voltage sparks arc over jumping across the rings. It's just too dangerous and complex.
So that design is basically limited to small, low-power stuff.
Right, like the alternator in an old car. For the big stuff, for the grid, the industry uses the rotating field alternator.
The elegant inversion, as you called it.
It really is. In this design, they flip it. The armature winding, where the dangerous high voltage is generated, is now stationary. It's built into the stator frame. And the magnetic field windings, which only need low voltage DC to work, are put on the rotor.
Okay, this is where it gets really interesting. What is the single biggest advantage of making the magnet spin instead of the output coils?
It completely solves the high voltage problem. The thousands of volts are now being generated in stationary coils, so you can connect to them directly with heavy, fixed bus bars on the stator frame. It's infinitely safer and simpler.
The insulation is easier, cooling is better.
Everything is easier, maintenance, everything. The dangerous part isn't moving anymore.
Okay, so we've taken the high voltage problem off the rotor, but the rotor still needs power to become a magnet, right?
It does. It needs a steady supply of low voltage direct current, usually around 125 or 250 volts DC, to create that fixed polarity magnetic field. And because it's low voltage, feeding that into the spinning rotor through slip rings is perfectly safe and manageable. The risk of a dangerous arc over is gone.
Which brings up a really cool piece of this puzzle that most people don't know about. The exciter generator. The DC has to come from somewhere.
The exciter is this fascinating little system within a system. Large alternators have a small, dedicated DC generator built right onto the same shaft. Its only job in life is to produce the stable DC current needed to excite the main rotor's field windings.
Wait, so there's a small generator whose only job is to power the magnet for the big generator. Why not just use batteries or something?
It's all about stability and control. The sources point out that these exciters are often shunt-wound and self-excited, which is a fancy way of saying they are designed to produce a very stable DC voltage that doesn't fluctuate much as the main generator speeds up or slows down slightly.
So it's a regulated power supply.
A meticulously regulated power supply, because the strength of that DC current directly controls the final output voltage of the main alternator. There's usually an automatic voltage regulator, an AVR, that's constantly monitoring the grid voltage.
Ah, so it's a feedback loop. If the grid voltage sags a little bit, because a lot of people turn on their air conditioners.
The AVR senses that sag and immediately tells the exciter to send a little more DC current to the main rotor's field.
A stronger magnetic field induces a higher AC voltage, and the grid voltage comes back up.
Exactly. The exciter is the tool for controlling voltage. This is critical. It allows for independent control over the two most important parameters. Frequency is controlled by speed, and voltage is controlled by excitation. That separation of control is another huge reason the rotating field design is the standard.
Okay, so we've established that the 60 Hz frequency is fixed, and we see how the machine is designed to handle the high voltage. Now we get to the absolute core of it. How do you generate a fixed 60 Hz when your input speed could be anything from a fast turbine to a slow water wheel?
The key, the decoupling element, is the number of magnetic poles built into the rotor. This is the single most important variable. It's what allows an engineer to design a machine that translates, say, 900 mechanical rotations per minute into the electrical equivalent of 3,600 cycles per minute.
And this relationship is all laid out in one simple, elegant formula.
Let's talk about something that holds back even the smartest people from really succeeding in fields like engineering, physics, you name it. It's not about how smart you are, and it's not about passion. It's a single, fundamental roadblock that most people just don't see coming. So why is that? Why does someone who can grasp these incredible, complex theories in electronics or advanced mechanics suddenly hit a wall? What is this invisible barrier that just stops so many talented people right in their tracks? Well, this quote from a veteran engineer just hits the nail on the head. All of that incredibly advanced, mind-bending stuff, it's all built on the algebra you learned in high school. But here's the catch, and it's a big one. You can't just kind of know it. You have to really know it, inside and out. And that brings us to the main point here. The foundation isn't just important, it's everything. It's the bedrock that every single advanced skill is built upon. Let's break down why this is so unbelievably critical. Okay, so before you can even think about manipulating something like derivatives in calculus, you have to be an absolute wizard at shuffling equations around. And that's pure algebra, right? Or what about mastering imaginary units for electrical engineering? They're not just some weird abstract idea, they're a vital tool. And using them, yep, that depends entirely on how solid your algebra is. And then you've got vectors and polynomials in physics. That's the language of the field. Trying to work with them without a fluent command of algebra it's like trying to write a masterpiece novel when you don't even know the alphabet. So the bottom line is this. You need an absolutely unshakable foundation. When you're wrestling with some big, hairy, complex problem, the very last thing you want to be worried about is whether you made a simple algebra mistake. That right there, that is the hurdle. So if a shaky foundation is the real problem, what's the solution? Well, this is where a tool built specifically for this comes in. And today, we're going to look at one called Algeprime because it's designed to fix this exact problem. So what is Algeprime exactly? Think of it as a super comprehensive, high-end video series that's all about one thing, building your algebra foundation from the ground up so it's rock solid. It's not just a review, it's a complete rebuild. But here's the thing, Algeprime isn't just a bunch of videos. It's a whole structured system, a method designed to get you to true mastery. Let's take a look at how the Algeprime method actually works. The Algeprime method really rests on these 4 pillars. First, it's guided learning. It's a journey where every single step logically builds on the last. Second, it's all about practical relevance, so you actually see how this stuff shapes the real world. Third, the explanations are amazing. They just break everything down into simple, digestible steps. And finally, you can track your progress with these cool interactive checkpoints, which really helps you stay on track. And like I said, this isn't just about watching videos. Algeprime gives you a complete toolkit, everything you need to actually succeed. So what's in the box? With Algeprime, you get interactive problem sets and quizzes to really sharpen your skills. You get downloadable reference materials, you get access to a community for support, and you get unlimited access to all 150 episodes. And you can watch them anywhere, on your phone, on your desktop, wherever. But on top of all those features, the people behind Algeprime do something that really shows how much they believe in their program. It comes down to this number, 60. It's a 60-day, no questions asked money-back guarantee. I mean, that means there is literally zero risk for you. You can try Algeprime, go through everything, and if it's not what you need, you get a full refund. It's really that simple. Okay, so if you're feeling like, yeah, this is me, my foundation needs work, Algeprime has a few different ways you can get started. Let's look at the learning paths you can choose. You've got a few options here. The weekly plan is awesome if you just want to dip your toes in and see what Algeprime is all about. If you're ready to commit a bit more, the intro or intermediate packs are great. And for those who are all in on total mastery, the full series gives you everything. It's really just about what works for your goals and, your budget. Look, the advanced stuff is the fun part. I get it. But it's mastering the fundamentals that really unlocks your potential. So please, don't let this one single hurdle hold you back from the future you want. You can fix this. The first step is super easy. Just head over to algeprime.com to check it out for yourself. That's ALGEPRIME.com. See if Algeprime is the tool you need to finally build that foundation for good.
Formula.
The defining formula for AC generation. Frequency equals the speed of rotation, n times the number of poles, p, all divided by 120.
F equals N times P over 120, where F is in Hertz, N is in RPM, and P is the total number of poles.
That little equation is the entire answer to the paradox. I mean, look at it. If F has to be a constant 60 hertz, then the product of N, your speed, and P, your poles, also has to be constant.
So if your speed, N, goes down,
your number of poles, P, must go up by the exact same proportion to keep the output at 60 hertz.
Okay, let's talk about that constant, 120. It feels a bit random just sitting there. Why 120?
It's just a conversion factor to make the units work out, but it's a really important one. It actually combines 2 different conversions. First, remember how we said one electrical cycle requires a north pole and a south pole to pass the coil?
Right, you need a pair of poles for one full cycle.
Exactly. So the P in the formula is a total number of individual poles. To get the number of effective cycles per revolution, you have to divide P by 2 to get the number of pole pairs. So that's where the 2 comes from.
Okay, so that's part of the 120. What's the rest?
The rest is time. The speed, N, is in revolutions per minute, but frequency, F, is in cycles per second. To make those match, you have to divide the minutes by 60.
So, 2 for the pole pairs, times 60 for the seconds. That's a 120.
That's your 120. It's the constant that connects the mechanical reality RPM with the magnetic geometry and the required electrical output in hertz.
That makes so much more sense now. It really shows that rotational speed alone is not enough. You need the geometry.
So let's run the numbers. Let's take the simplest possible generator. 2 poles, one north, one south.
Okay, P equals 2. We can rearrange the formula to solve for the speed we need. So N equals F times 120 divided by P.
Plug in the numbers.
60 hertz times 120 is 7,200. Divide that by 2 poles, you get 3,600 RPM.
And there it is. For a 2-pole machine to make 60 hertz power, it must spin at exactly 3,600 RPM. That's the synchronous speed. That's your gas turbine.
But now for the elegant part, the solution for the slow-moving hydroelectric dam. You just start adding poles.
It's this incredible multiplier effect. The more poles you add, the more electrical cycles you get for each single mechanical revolution. Let's look at those examples from the sources.
Okay, to keep that 60 hertz output, if we use a 4-pole generator,
the speed required is cut in half. N equals 7,200 divided by 4, which is 1,800 RPM.
and if we double it again to an 8-pole generator,
Speed is cut in half again, 900 RPM.
and for some of the really big, slow hydro turbines, they might need something like, what, a 20-pole rotor?
Exactly, and a 20-pole rotor would only need to spin at 360 RPM to produce perfect, grid-stable 60 hertz power.
That is the answer. The slow-moving giant compensates for its lack of speed with sheer magnetic complexity. More poles, more cycles per turn.
And that very requirement, the speed of the prime mover, ends up dictating the entire physical design of the rotor itself. It creates this clear divide in how you build these things.
Right, the high-speed rotors versus the low-speed ones.
Let's start with the fast ones, the turbine-driven rotors. These are for steam or gas turbines, so they're running at 1,200 RPM or more typically 1,800 or 3,600 RPM.
So they only need 2 or 4 poles. What does that speed demand from the actual structure?
Well, think about the forces. The centrifugal force at 3,600 RPM is just astronomical. So these rotors have to be long, thin, and cylindrical. They look like a solid steel drum. They're often forged from a single massive piece of high-strength steel.
And the windings.
The copper windings are buried deep inside machine slots and held in place with incredibly strong wedges and retaining rings. If they weren't, the force would literally rip the copper right out of the rotor. The entire design is about surviving those immense rotational stresses.
And then you have the complete opposite, the salient pole rotors you find at the GAMs.
These are for low-speed jobs, under 1,200 RPM. They're paired with things like water wheels or big diesel engines, and salient just means projecting or prominent.
Because you can actually see the individual pole pieces.
Right. They look like a series of distinct magnetic poles bolted onto a central frame. It's a very different construction.
And I can see the immediate engineering problem there. You can't spin a rotor with big, heavy things bolted to it very fast.
You absolutely cannot. Salient pole rotors have to be much wider, a much larger diameter than the skinny turbine rotors. And that large diameter means that even at a slow speed, the centrifugal force on those bolted-on poles is enormous. If you tried to spin one at 3,600 RPM, it would just fly apart. The poles would tear right off the frame.
So the trade-off is perfectly clear. The slow speed of the water dictates a salient pole design, and that design's physical limits force you to use a high pole count to hit the required 60 hertz.
That's the bridge. The pole count is the engineering that connects the mechanical reality of the prime mover, whether it's a screaming turbine or a slow, massive water wheel, to the rigid, unchangeable electrical demand of the grid.
We've nailed down frequency, but efficient power generation needs more than just a single output. We need to scale up, which brings us to multi-phase power. And when we say phase, we're really just talking about a voltage, right? And its timing.
Correct. A single-phase alternator, which we've mostly been discussing, produces one single sine wave of voltage. It's fine for your desk lamp or a small appliance, but if you're trying to run a factory, single-phase power is really inefficient.
So to help us understand the industry standard, which is 3-phase, our sources use the 2-phase alternator as a kind of stepping stone.
It's a great illustration. In a 2-phase machine, you just put 2 separate armature windings in the stator, but you place them 90 degrees apart physically.
So because they're mechanically offset?
The voltages they produce are electrically offset. They're 90 degrees out of phase. So when voltage A is at its peak, voltage B is at 0. Then as voltage A falls, voltage B rises. They're perfectly staggered.
What's the advantage of that?
Well, you're getting two power sources from the same machine using the same rotating magnet. It's more efficient. And the sources highlight this cool wiring trick, the three-wire connection. You can connect the two phases together and create a third output.
And that third output voltage is special.
It is. It's the vector sum of the two individual phases. And because they're 90 degrees apart, you can't just add them. You use vector math, and the result is a combined voltage that is 1.414 times bigger than either of the individual phase voltages.
That number, 1.414, that's the square root of 2, isn't it?
It is. It's just a result of the Pythagorean theorem applied to the 90-degree electrical angle. It's a neat way to get a voltage boost just from geometry.
But two-phase is mostly a historical footnote, because the real sweet spot is the three-phase alternator.
The three-phase machine is the global standard. You have three separate armature windings, but this time they're spaced 120 degrees apart around the stator.
And that creates three voltages, each 120 degrees out of phase with the others. Why is 120 degrees the magic number?
It provides the smoothest, most constant power delivery possible. With the phases evenly spread over the 360-degree cycle, at any single moment in time, the total power being delivered by all three phases combined is constant. It never drops to zero.
Which is huge for big motors, right?
Yeah.
No pulsating torque.
Exactly. It's smoother, more efficient, and you actually need less copper to transmit the same amount of power compared to single phase.
And this setup gives engineers two main ways to wire the phases together.
Yeah.
The Y connection and the delta connection.
Right. The Y, or Y connection, is also called a star connection. You take one end of each of the three windings and connect them all to a common neutral point. It literally looks like the letter Y.
And the main characteristic here is a voltage boost.
Yes, another magic number, 1.73, that's the square root of 3. Because of the 120-degree displacement, the voltage between any two of the outer lines, the line voltage, is 1.73 times bigger than the voltage in any single phase winding.
Okay, so you get higher voltage for transmission.
But the trade-off is that your line current is the same as your phase current. So high voltage, same current.
And the other option is the delta connection.
With delta, you connect the windings end-to-end in a closed triangle, like the Greek letter delta. Here, the line voltage is exactly the same as the phase voltage, no boost.
So what do you get instead?
You get a current boost. The current flowing out on the line is 1.73 times greater than the current in any single winding. So this is often used for distribution systems where you need high current capacity.
The sources have a great real-world example of this. Power on a ship.
It's a perfect little model of the main power grid. A big naval vessel generates power at 450 volts, three-phase. That's the most efficient way to run the huge motors for propulsion and pumps.
But the coffee maker in the galley doesn't run on 450 volts three-phase.
Exactly. It runs on standard 117 volts single-phase power. So they use step-down transformers to convert the high-voltage three-phase power down to the low-voltage single-phase power needed for all the smaller equipment around the ship.
So we have frequency control, we have phase control. What about just controlling the output voltage second by second?
As we touched on with the exciter, the voltage produced depends on three things. Number of conductors, which is fixed, speed of rotation, which is fixed to maintain frequency, and the strength of the magnetic field.
So the only variable left to play with is the magnetic field.
That's the throttle. You control the alternator's output voltage by adjusting the DC excitation current flowing to the rotor. The automatic voltage regulator does this constantly, strengthening the field when voltage sags and weakening it when voltage rises.
This brings us to how these machines are rated.
So you want to grow on YouTube? Let's talk about the new AI toolkit that's changing everything. You know that feeling, right? You pour your heart into a video and get literally 0 views? But what if you could get an unfair advantage, a way to work smarter, not just harder? It's a simple workflow: idea, script, video. But now AI is supercharging every single step. It all starts with the idea, and honestly, this is where most creators fail. vidIQ helps you find those golden keywords, topics with high search volume but low competition. It'll also audit your channel, feed you daily ideas, and even spy on your competition. And yeah, it's not some secret. Over 20 million creators are already using this strategy. Okay, you've got a killer idea. Now what? You've got to write a script. Well, that's where TubeMagic comes in. It's an AI that literally writes viral scripts for you. It can match your voice, use the latest AI models, and even learn from other successful videos. And creators are loving it. They've already generated over 200,000 scripts with it. All right, idea, check. Script, check. Now for the hard part, actually making the video. Or maybe not so hard. Vid.ai takes that script and turns it into a finished video. And I mean everything. The voiceover, the visuals, the background music, even the captions. The best part, you don't need a camera. You don't even need to know how to edit. So you see how this all connects? It's not just 3 tools. It's a complete ecosystem. They do all the boring work so you can just focus on being creative. So you go from vidIQ for strategy, to TubeMagic for the script, to vid.ai for the video. It really makes you wonder, with tools this powerful, what's next for content creation?
Machines are rated. We think of power in watts, but alternators are rated in kVA, kilovolt amperes. Why is that?
Well, the useful power a load consumes is in watts or kilowatts, but the alternator doesn't care about the load's efficiency. The alternator's physical limitation is heat.
The heat generated in its own windings.
Right. And that heat is purely a function of the current flowing through the windings, the I²R loss. The insulation can only handle so much heat before it fails. So the manufacturer rates the machine based on the maximum current, the maximum amps it can safely handle. Volt amps, or kVA, is a measure of that thermal limit, regardless of how much useful work that current is doing.
The genius of the generator, that fixed relationship between poles, speed, and frequency, it has this direct, unbreakable consequence for every single machine that uses that power.
Absolutely. We move from the source to the consumer, the AC motor. And that same frequency formula now dictates the motor's speed.
We can just flip the formula around. Speed N equals 120 times frequency F divided by the number of poles P.
And since the grid frequency F is locked at 60 Hertz, the theoretical top speed of any AC motor is determined only by the number of poles built into its stator. A 4-pole motor will always have a synchronous speed of 1800 RPM. A 20-pole motor, 360 RPM. It's fixed by its construction.
And for some motors, synchronous motors, they actually lock onto that rotating field and spin at exactly that speed.
They do, but they're not the most common type. The real workhorse of the world is the induction motor. And these motors rely on a really fascinating concept called slip.
This part is so counterintuitive. The rotating magnetic field in the motor stator induces a field in the rotor, which makes the rotor spin. But the rotor is never allowed to catch up.
It can't. It's physically impossible. If the rotor were to spin at the exact same speed as the magnetic field at synchronous speed, then from the rotor's perspective, the magnetic field would be stationary.
No relative motion.
No relative motion. And Faraday's law says if there's no relative motion, there's no induced voltage in the rotor. No voltage means no current. And no current means no torque. The motor would just start producing power.
So to create torque, it has to be constantly falling behind. That lag is the slip.
Slip is just the difference between the synchronous speed of the field and the actual speed of the rotor. In order to do any work, the rotor must constantly be slipping behind the field that's pulling it along.
And the amount of slip changes depending on the load.
Directly proportional. If you put a heavy load on the motor, it needs to generate more torque. To generate more torque, it needs a stronger induced current in the rotor. And to get that stronger current, the relative speed between the field and the rotor has to increase. So the rotor slows down just a tiny bit. The slip increases.
So a motor with a synchronous speed of 3,600 RPM might run at 3,450 RPM under full load. That 150 RPM difference is the slip it needs to do its job.
Exactly. And this reliance on slip means that if the grid frequency were to drop, even by a little, the synchronous speed of every motor on the grid would drop instantly, causing all sorts of industrial process problems.
This brings us to the history of it all. How do we even settle on 50 and 60 Hertz? Because that decision locked in all these speeds and pole counts for the next century.
The late 19th century was total chaos. Our sources call it a frequency jungle. Different power companies were using all sorts of frequencies, from as low as 16 and 23 hertz all the way up to 133 hertz. The final choice of 50 and 60 was a huge engineering compromise.
What were the competing interests? What was the fight about?
Well, on one side, you had heavy motors and long-distance transmission. They wanted low frequencies. It reduced power losses over long lines and worked better with the big, early traction motors for trains.
Okay, so low frequency for industry.
Then on the other side, you had lighting and transformers. They wanted high frequencies. A higher frequency meant no annoying visible flicker in the lights, and more importantly, it allowed them to build much smaller, lighter, and cheaper transformers.
It sounds like an impossible fight to resolve.
It was. But people like George Westinghouse in the US saw 60 hertz as a really good middle ground. It was high enough to get rid of most of the light flicker and allow for reasonably sized transformers, but it was still low enough to be pretty good for motors and transmission.
And the sources mentioned the original Niagara Falls generators as a case where industry won out at first.
That's a classic example. The first generators at Niagara Falls in 1895 were designed to produce 25 hertz power, a very low frequency. That was a deliberate choice to power the heavy industrial motors in nearby Buffalo. You could still use it for lighting, but the flicker was apparently very noticeable.
And so these two standards, 50 and 60 hertz, eventually just won out through market forces.
Pretty much. In Europe, companies like AG heavily promoted 50 hertz, and it became the standard there. In the US, Westinghouse's push for 60 hertz, combined with a huge boom in the residential lighting market, cemented that as the standard. And once those standards were set, that formula F equals NP over 120 became the law of the land for every engineer designing anything that connected to the grid. So to pull it all together, that paradox we started with, the slow generator making high-frequency power, it's solved entirely by the clever engineering of the magnetic field. The secret to getting a stable 60 hertz, whether your engine is a 3600 RPM turbine or a 90 RPM water wheel, is just building the rotor with the right number of magnetic poles. The generator becomes a translator, converting mechanical speed into a fixed number of electrical cycles, with the pole count as the dictionary.
It's just a beautiful example of how a rigid standard forces these incredibly elegant engineering solutions. And that grid frequency isn't just maintained, it's meticulously regulated over the long term. Utilities will actually speed up or slow down their generators slightly over a 24-hour period to ensure that a precise number of cycles, exactly 5,184,000 for a 60 hertz grid, occur each day. So the grid itself becomes a clock. With that in mind, what common household device relied completely on this incredible electrical stability to perform its main function, working far better than it ever could on simple DC power?
The answer is the classic old-fashioned electric clock with the sweeping second hand. It uses a tiny synchronous motor, and the speed of that motor is locked directly and precisely to the utility frequency. By making sure the total number of cycles per day is perfect, the utility company is, in effect, regulating time for every one of those clocks plugged into the wall. Even if the frequency fluctuates for a moment, they correct for it later, ensuring those clocks keep almost perfect time. The grid itself becomes the world's biggest, most stable clock.